Okay, so I've shared a new Jamboard with you guys called the Complete Respiratory System Jamboard. And I want to add to that and complete our understanding, the initial understanding of the respiratory system leading into talking about vaping, cigarettes, etc. So let's go ahead and go to our second slide. And I want to grab a tool over here. I just want to trace the pathway of of air through, I chose a mucus color that's uninfected. It's usually yellow, and when it's infected, it turns green. So here we go. Let's go ahead and trace the pathway of air. It's going to go in through the nasal oral cavity, down the pharynx, which is a shared opening for food and air, past the larynx, down the trachea, and now it's going to divide into one of two bronchi. It's going to divide into the two bronchi and just continue it to get smaller and smaller and smaller until it reaches something called an alveoli. And there's about 400 million alveoli in your lungs. So we're going to have a lot of really tiny little branches called bronchioles because alveoli end at the end of a bronchiole like that. It kind of looks like a grape cluster. Okay, that's a bronchiole. All right, let me show you this animation. This is super short, but it shows the alveoli in your lungs. All right, so they are covered in blood vessels, which we'll get to the importance of that in a second. All right, let's continue to move on. Let's go here. So your entire respiratory tract is lined with mucus and with these little hairs called cilia. And when you're a smoker, you singe those and you make them ineffective. That's why people who smoke are at higher risk of respiratory illness. So let's figure out why. As this very brief video is playing, I want you to answer these two questions. Why do we need mucus, and how do mucus and cilia work together?
The air we breathe contains foreign matter such as dust, bacteria, and pollen. Hair-like cells called cilia, as well as goblet cells, can be found in the lining of the respiratory tract called the respiratory epithelium. Goblet cells secrete viscous mucus that forms a layer to trap foreign material. The wave-like action of the underlying cilia mobilizes the mucus layer, removing the foreign matter and preventing it from entering the lungs.
Okay, remember, that is your ultimate goal. You want to keep foreign matter out of your lungs. Liquid would be drowning, or if you were to get a virus or a bacteria in there, you could get a lung infection like pneumonia or bronchitis, etc. So you want to have that cilia to be sticky to absorb those molecules before they get into your body. Now, if that is unsuccessful, then your body will turn to another line of defense, which is more intense, which is a fever. It's going to try to zap those foreign bodies with heat. All right, let's move on. So before we get into the details about just respiration in general, we have to understand one common concept is, why the heck do we need oxygen? And whenever I ask that question, my students say to breathe, which is circular reasoning. Why do we need to breathe? What is the purpose of having oxygen in your body? So we're going to take a second and focus on that. So I'm going to keep this simple. Sorry, you guys are working on the formative as I was recording this in efficiency. So your cells have to have oxygen. If they don't have oxygen, they are going to die. Oxygen and food are the fuel that keep your cells working. And if your cells don't work, it's a massive ripple effect. The tissues die, the organ dies, the system it's a part of dies, and ultimately the organism, if the person is suffocating for lack of oxygen. So what is it about oxygen that's so important? Let's go here. Okay, oxygen. So you take food, and it could be sugar, protein, fat, could be a lot of different things. So this one's sugar. You take sugar and you combine it with the oxygen you breathe in your body cells. This is all happening in your cells. If you remember specifically from a previous science class, it's happening in something called the mitochondria, which is a little organelle inside of your cells. Combines with oxygen to produce carbon dioxide that you breathe out, water that you urinate out, and usable energy that is in the form of ATP. So without oxygen, you wouldn't have energy, and then the body part that the cell is deprived of oxygen would ultimately die. So if the liver cells didn't get oxygen, eventually the liver would die, etc. Okay, so how do we get oxygen to your body cells? Well, you have to have blood. If you didn't have blood, it would be like having Amazon, which is your lungs, without delivery drivers, which would be your blood. So the heart pumps the blood and that delivers the oxygen to your body cells. So this is a kind of a cool museum exhibit of all of your blood vessels kind of dyed red. So here it is in a more medically professional picture. Underneath your skin, blood that doesn't have a lot of oxygen and it looks to be blue or green underneath your skin, but the minute oxygen hits your blood, it turns red. Okay, so your blood transports your oxygen to your body cells through blood vessels, and blood vessels have a few different names: veins, venules, capillaries. These are going to be your smallest. That's probably the most important. Oh man, I'm not that good with writing with this. I'm just going to cheat and just write small instead of the smallest. They are the smallest blood vessels in your body. Okay. Sometimes you may have even had a broken capillary on your skin, just that little red pool of blood under your skin. Nothing harmful, usually goes away on its own, but that's what a capillary is. Okay, so let's see. Let's look now at the alveoli. I know I already showed you guys this animation. I love that image. It shows you all those little air sacs, and those are covered in blood. Those are covered in blood. So this right here, here's one alveoli. So this is an alveoli. They're the exact same thing. So let's see. This picture is the same as that picture, which is the same as that picture down here. Okay. These are alveoli, and here is going to be a bloodstream. So I'm just going to go ahead and label this right here. This is going to be blood. So this part right here is the most important connection for this class today. In your alveoli, oxygen diffuses into your bloodstream right here. So it goes from inside this air pocket and it diffuses into your bloodstream. All right, I'm not going to even fill out this picture right here because I don't want to make it more complicated than that for this class. So now we have the air sac. The air sac is where oxygen meets the blood. Now we have to figure out in the blood, how exactly do we get oxygen to stay there? So it's going to be with right here, red blood cells. Remember, red blood cells are only 45% of your actual blood volume. The other part is something called plasma and white blood cells. So 45% of your blood is red blood cells or are red blood cells. And the most important part about oxygen in red blood cells is what it attaches to, called hemoglobin. So pretend these are cars. Red blood cells are going to be like the oxygen Uber of your body, and it's going to carry the oxygen to the body cells so they can use them to make energy. So how exactly do they get there? And we're going to make some health connections in a second. They're going to use something called hemoglobin. It is a square protein. So I'm going to go ahead and put a square in here. Let's see. I'm going to insert a square. It looks like this molecularly, but we're just going to keep it simple. We're going to label it hemoglobin. Like that. Okay, so this is going to be your hemoglobin. This picture is flawed. It shows one hemoglobin per red blood cell, but really there's millions of them. So on a hemoglobin molecule, in each of the four corners of the square-shaped protein, you have an atom called iron. There's about, I think, 130 atoms on the planet. One of them is iron. So the chemical symbol for iron is kind of annoying that it's not related to its actual spelling. It's capital F, lowercase e, which stands for iron, so F. Let me type in here for some reason. Let's see. Fe equals iron. So there are 4 irons per hemoglobin. I'm going to put one right here. Fe. Pasted it. If it's in the 4 corners, it's fine. Fe, that one's actually perfect. There we go. Give me a second to catch up. So you have 4 irons. You're like, well, who cares? Okay, so iron is magnetic, and it's going to magnetically attach oxygen to it. So iron is important because it is the oxygen magnet that holds the oxygen on your blood. So iron is the oxygen magnet that keeps oxygen attached to your blood on its journey to your body cells. careful. And there's a... Okay, sorry. There we go. So you definitely need iron. Okay, I'll get to what anemia is in a second. If you don't have iron, you're not going to get enough oxygen to your body cells, and you could have some really bad results from that. So let's go ahead and just take a color, and then let's go ahead and attach our oxygens. We'll make that red. Go ahead and put your oxygens, which is O, over the top of your irons like that. These are going to be your oxygens. It's going to be for someone who's healthy. So now in your oxygen Uber on your hemoglobin, you can have 4 passengers. You can have 4 oxygens, and you can zip it and deliver it to your body cells. Well, some people don't have enough iron in their diet, or they are naturally genetically iron deficient. So the problem with this, you guys, is that they can get something called anemia. Here are some signs of anemia. You're always tired, shortness of breath, you're always sick. Pica is interesting. That's where you crave strange things like concrete, paper. That's your body telling you you need iron. Pallor, which is have a really pale under eyes. I'll show you this image right here. That's anemic right there. If you like lift down on your lower eyelid and it's really pale, that could be a sign of anemia. Okay, cold hands and feet. All of this is because you either don't have enough red blood cells, which means you don't have enough oxygen Ubers, or you don't have enough iron, which is how many passengers the hemoglobin can hold. So that's problematic for people. Sometimes I know for me, my body tells me you need to eat steak because that has a lot of iron in it. If you don't eat steak or meat, you can have dark leafy greens. But if you're feeling this way, always tired, cold hands and feet, you might have anemia, which is either low blood or low iron. And you need iron so you can have oxygen delivered to your body cells. If you don't have oxygen, you're going to start to feel the symptoms of anemia. Okay. Anemia, check. Okay, and then the diaphragm. Sometimes with the diaphragm, a picture paints 1,000 words for me. This is a large sheet-like muscle. It's dome-shaped like a parachute. It's very thin. It pulls down when you breathe in, and it pushes up when you breathe out, and it just opens up the lungs, relaxes and releases the lungs. Here's an image right here. Okay, air goes in, air goes out. And when that contracts out of pace, that's something called a hiccup, which we've all been affected by. And the voice sound that it makes is because it causes the larynx to also trip as well. Okay. I believe that is the end of the respiratory system. I wanted to show this video on how oxygen spreads through the body. It does a good job pulling everything together.
You breathe in about 17,000 times per day. It's a process you rarely think about, but behind the scenes, a huge coordinated effort is playing out. Your vital organs, the gut, brain, bones, lungs, blood, and heart, work together to sustain your life by delivering oxygen to tissues throughout your body. Most of our cells need oxygen because it's one of the key ingredients of aerobic respiration. That's the process that produces a molecule called ATP, which our cells use to power their many incredible functions. But getting oxygen throughout our bodies is a surprisingly difficult task. Gas enters cells by diffusing in from their surroundings, and that only happens efficiently over tiny distances. So, for oxygen to reach the cells within our bodies, it needs a transportation network. This is where our 20 trillion red blood cells come in. Each one contains about 270 million oxygen-binding molecules of hemoglobin, which is what gives blood its scarlet hue. To make these cells, the body uses raw materials that become available from the food we eat. So in some ways, you could say that oxygen's journey through the body really begins in the gut. Here, in an amazing display of mechanical and chemical digestion, food gets broken down into its smallest elements, like iron, the building block of hemoglobin. Iron is carried through the cardiovascular system to the body's hematopoietic tissue. This tissue is the birthplace of red blood cells, and it can be found enclosed within our bone marrow cavities. The kidneys regulate our levels of red blood cells through the release of erythropoietin, a hormone which causes marrow to increase production. Our bodies churn out roughly 2.5 million red blood cells per second, a number equivalent to the entire population of Paris, so that oxygen that makes it to the lungs will have ample transportation. But before oxygen can even reach the lungs, the brain needs to get involved. The brainstem initiates breathing by sending a message through your nervous system, all the way to muscles of the diaphragm and ribs. This causes them to contract, thus increasing the space inside the ribcage, which allows the lungs to expand. That expansion drops your lungs' internal air pressure, making air rush in. It's tempting to think of our lungs as two big balloons, but they're actually a lot more complicated than that. Here's why. The red blood cells in the vessels within your lungs can only pick up oxygen molecules that are very close to them. If our lungs were shaped like balloons, air that was not in direct contact with the balloon's inner surface couldn't diffuse through. Luckily, our lungs' architecture ensures that very little oxygen is wasted. Their interior is divided into hundreds of millions of miniature balloon-like projections called alveoli that dramatically increase the contact area to somewhere around 100 square meters. The alveolar walls are made of extremely thin, flat cells that are surrounded by capillaries. Together, the alveolar wall and capillaries make a 2-cell thick membrane that brings blood and oxygen close enough for diffusion. These oxygen-enriched cells are then carried from the lungs through the cardiovascular network, a massive collection of blood vessels that reaches every cell in the body. If we laid this system out end to end in a straight line, the vessels would wrap around the Earth several times. Propelling red blood cells through this extensive network requires a pretty powerful pump, and that's where your heart comes in. The human heart pumps an average of about 100,000 times per day, and it's the powerhouse that ultimately gets oxygen where it needs to go, completing the body's team effort. Just think, this entire complex system is built around the delivery of tiny molecules of oxygen. If just one part malfunctioned, so would we. Breathe in. Your gut, brain, bones, lungs, blood, and heart are continuing their incredible act of coordination that keeps you alive. Breathe out.